Okay, I want to start talking a little bit more about some more musical instruments. We're going back to this little animation here. We can have stringed instruments, which we talked a little bit about earlier, but we can also have things like flutes and saxophones, and these are called tubes. And they have basically, you vibrate standing waves in air, columns of air, tubes of air. And some of these tubes can be considered to be open tubes. And open tubes basically means it's open on both ends, And we can have what we call closed tubes, which actually means it's open only on one end. So closed tubes doesn't mean that they're all just completely closed off. It means one end is open and one end is closed. Wherever you have a closed end, that's called a fixed end, and there should be a node at that end. When you have an open end, that's an antinode, or what I call a loop. The air is allowed to oscillate back and forth at that end. So that would be an antinode, but at a closed end you have to have a node. So we want to look at look at this here to see how some fundamental vibrations occur. And then I'll do a couple follow-up videos on closed tubes and open tubes to see how this applies. So this first example we had, remember the string, and it's clamped on both ends. It has two fixed ends. A string has two fixed ends, not like the tubes. They have two fixed ends, and so the most fundamental way that this string can vibrate, so waves are going to go down, they're going to interfere with waves coming back and forth, and you get a resulting standing wave, and the fundamental way that it can vibrate is like this. That's it. Now, and you'll notice that for this frequency, whatever this frequency is, and it says right here, 0.067, the wavelength is that from here to here would just be like a crest, or it would just be a trough, one of the two. And you need a crest and a trough. So the wavelength actually is twice the length of this string. Okay, so I could actually measure that. I could take it times the frequency, and I'd actually know the velocity of this wave. Okay, so if I want to I can get other standing waves to form in here. There's different modes of vibration that you can get a string to vibrate at. I want to go to the next harmonic. The next harmonic would be double whatever this frequency is. And of course, if you're doubling the frequency, you should be cutting the wavelength in half. So if I click the next harmonic, now you see I have a crest and a trough. So this whole distance from here to this end here is one wavelength, however long that is. And so originally the wavelength was twice this distance. Now it's just this distance. So the wavelength was cut in half because the frequency was doubled. But you can see that this would be called the second harmonic, right? So I took 2 times the fundamental frequency and I get the second harmonic. I can click the next harmonic, and now I took that original fundamental times 3, and I got the third harmonic. And you still have a node on the end and a node on the other end. Now you have some nodes here in the middle, right? But there's 1, 2, 3 loops. I can get the fourth harmonic. Now I have 4 loops. And what's a wavelength? The wavelength would be from here to right here, right? There's a crest and the trough right across there. Okay? So the point is, with strings, you can get every single harmonic. Because I have a node on one end and a node on the other, I can keep clicking the next harmonic, and now I have 5. The fifth harmonic, so it was 5 times whatever that original frequency is. 0.334 is 5 times 0.067, right? That's my fundamental. Okay, so that's strings. All right, let's look at some musical instrument that has an open end on either end. If I was in class, I'd have like an aluminum rod, a simple aluminum rod. I could actually whack the end of it, and I could get that rod to sing. I could actually get it to play a certain fundamental frequency. Now, that's an open tube. It has open ends. So there wouldn't be nodes at the end. This thing here would be allowed to vibrate up and down and up and down, and this one over here would be able to go up and down and up and down. But ironically then, in the middle, is where the waves that are going back and forth would actually cancel out, and you would have a node in the middle. So if I look at 2 open ends, this is what I get instead. I have open on the end, oscillating back and forth. This is open on this end, and there's a node here in the middle. Okay, and it says the frequency is 0.067. How long is a wavelength here? Okay, so from from here to here, you'll notice that this is up to the crest and then down to the bottom of the trough. That's actually half of a wavelength. That's exactly like it was with the strings, right? The strings was half of a wavelength. So to get a full wavelength, I'd have to take this point here to this point here, and I have to multiply by 2, and I would have a full wavelength. Okay, so 2 open ends is kind of the same as 2 fixed ends. The difference is that with 2 fixed ends, you have nodes on the end. But with open ends, you have antinodes on the end. But you still get a fundamental frequency, and you can still get every harmonic. If I do the next harmonic, then I get this. And see, there's nodes in here now, right? And I have a full wave. So it starts down here as a trough, and when it does that, it ends over here as a trough also. Okay, so that's a full wavelength. My frequency doubled from what it was, and my wavelength was cut in half. So now it's just one full wavelength. I can do the next harmonic, and I get this. This is the third harmonic. And then I could get the fourth harmonic, and I could get the fifth harmonic. Okay, so I can get, again, every harmonic. I can get all harmonics with 2 fixed ends on the string. I can get all harmonics with 2 open ends on an open tube. All right, now the tricky part. Let's do one open end. Okay, so we have a closed end, we have an open end. So this is tricky because this is an odd node, and you have a node on this end, the closed end, but you have an antinode over here on the open end. Okay, so this is the fundamental way that a closed tube, column of air, could actually vibrate. On the closed end, it's the air molecules aren't allowed to move, but on the open end, they're allowed to vibrate back and forth. So you'd have, this is a closed tube fundamental vibration. Now, the key is here, what is the wave? How much of a wavelength do we have here? Well, we go from here and then up to the top of a crest. So we only actually have a quarter of a wavelength. A quarter of a wavelength. Okay? So, how would I find the full wavelength? Well, I'd have to take this distance from here to here, and I'd actually have to take it times 4. See, that's a difference. On the 2 fixed ends and the 2 open ends, I took the distance from here over to here, and I multiplied by 2 to get a full wavelength. But for a closed tube, like this is, I'd actually take this whole distance of this tube or whatever times 4 to get the full wavelength. Now, let's think about this here. What if I double this frequency to get the second harmonic? So that would make the wavelength be half, would be a half wavelength, right, if I doubled this thing. But the problem is with that is that that would have to come back. It goes up like this. It'd have to come back down to a node. And this is an open, or the closed tube, so it's open on one end. You can't have a node here. So you can't actually get this thing to vibrate at its second harmonic. I can't get this string here to vibrate at 0.0, what would that be, 68. I can't get that. In fact, watch, if I hit the next harmonic, what happens? It went up to 0.1, right? This next harmonic is tricky. That next harmonic wasn't the second. It's the third. Because see, now I can do, if I just pause it right, boom, right there, I have, you know, quarter of a wavelength, another quarter of a wavelength, right? That'd be the second harmonic. If I doubled this, I'd come down to here, but I can't let that happen because there's a node there. So it actually has to go down here, so there's another antinode here, back and forth. There's a node here, there's an antinode here at the end of the tube, and this stays as a node here. So that would be the third harmonic. 1, 2, 3. That'd be the third harmonic that I would have there. Okay. But if I click the next available harmonic, what would it be? Well, it can't be the fourth because that'd close this up again, right? So it has to be the fifth harmonic. Okay? So I got 1 quarter of a wavelength, another quarter of a length, that's 2, another quarter of a length at 3, another quarter of a length at 4, another quarter of a length at 5. That's 5 quarter wavelengths right there. Okay? So the wavelength of this tube vibrating at this thing would actually be, it'd be 4/5 of the entire length right here, because there's one full wave right there. Okay, so in review, Two fixed ends, you have two nodes on either end, you can get every single harmonic. Two open ends, you have two loops on the ends, antinodes on the end. You can again get every single harmonic. The wavelength, to find the wavelength of the fundamental, you'd have to take twice the length of the tube, right? For two fixed ends. And for two open ends, you'd also have to take twice the length of the tube. But for one open end, you can only get odd harmonics. You can get the fundamental, you can get the third, the fifth, the seventh, the ninth. You can only get odd harmonics, and you have to take 4 times the fundamental frequency to get the length of the wave. Okay, I'm going to draw that out a little bit in the next couple of videos, but hopefully that, if you can remember kind of that, then it'll make sense in the next couple of videos.